Hello everyone. Today we're going to use Dask array to interact with weather data using a traditional cluster. So our setup, we have NetCDF files on disk for one file per day. Those files are on a network file system for network storage, and we're using SunGridEngine to deploy our distributed scheduler. These three tools we often find used together in a lot of academic and research institutes. This is why we're using them all together today. We've set up our cluster today with Star Cluster. Just point to that website for a moment. If you Google Star Cluster, it's a nice way to set up a nice small cluster on EC2 and sort of play with it. It's a very common environment. We're using that same development environment here today, except that we've added an Anaconda. So today we're going to use our 4 nodes of our cluster, and we're going to load data from disk, from network file system, into memory. Those would be NumPy arrays in memory, spread around our cluster. Then we're going to logically collect all of those small NumPy arrays into a single Dask array that we are then going to interact with inside of a notebook. So we'll have some very nice interaction with this data set. It'll be very fast, and it'll be across data that's spread across a cluster. Okay, so the data we have is we have the global temperature, every quarter degree of latitude and longitude, recorded every 6 hours for about 5 months. This is the limit of what we could fit on the network file system that Star Cluster set up. It's not particularly large, but it's enough that it'll get the point across. So this is going from January until about mid-May in 2014. This is all from the European Center for Meteorological Weather Forecasting. So to load in the data, we're going to use the NetCDF library, which we just content installed. And there's a little function here which takes a file name and produces a NumPy array. So if we call that function on our first file names, we get out, indeed, a NumPy array. That NumPy array holds all of these different temperatures. Judging by the magnitude, I'm guessing these temperatures are stored in Kelvin. And so here's the temperature at various points on the Earth at various times for the 1st of January. We're going to look at the shape of that just to reinforce the dimensions that are happening here. So the dimensions here are time, latitude, and longitude. Time, as I mentioned, 4 here, because we're measuring every 6 hours over a 24-hour day. And then the latitude and longitude are every quarter degree of resolution for latitude and every quarter degree of resolution for longitude. Okay, so it's 180 times 4 and 360 times 4. Okay, so what we want to do is we want to call this load temperature function on all of our file names, not just the first one, but we want to use all of our workers, all of our machines in our cluster to load those files into memory across the cluster, not just on one machine. To do that, we're going to use Dask's distributed scheduler and workers. So we're going to set up that system on a different screen for a moment using SunGridEngine. So SunGridEngine is a standard job scheduler like Slurm or Torque or like PBS scripts. So here I'm logged into the cluster on one of the nodes, and I'm going to run the dscheduler command, which comes with distributed. So if you were to do pip install distributed, you would get these commands. That starts the scheduler on one node. Now that scheduler needs workers. So we're going to call qsub. We're going to say that we want to use binaries, not a script, and that we want to use our user environment. And then we're going to call the worker with this same address that the scheduler gave to us. And we're going to do that a few times. So we're going to start up 4 different workers, and hopefully that will be distributed across our 4 different machines. I'm using this -v here because I'm using not the system Python, but my own content installed Python. So great, it looks like over here we've seen that our 4 workers have connected, so SunGridEngine did its good job. It started our workers across the cluster. And it even looks like it chose different hosts for all of these processes, which is nice. It means that our work will be spread across evenly. We can go and look and verify that indeed our dworker processes are in a run state. So great. Now we can go back over here and we can grab this address we had from before, and it's the same address we're using here. This is where we put it for our client. So this executor object is the user client, and we can see that we're connected to the right scheduler. We have 4 workers, each with 8 threads. So this is the object that we're going to use to map our load temperature function across all of our different file names. So let's go ahead and do that. And so now all of our workers are pulling in data, and they are loading that data from NFS, and they're creating lots of little NumPy arrays in RAM. So we get back from that a bunch of futures, where each of these futures corresponds to one NumPy array stored on one of the workers. And if we wanted to, we could get out one of them and ask for the result and actually pull the data back, which will take a moment, but here we get the result back. So it is indeed pointing to a NumPy array, but this data is actually living out on a remote cluster. It's not inside of our client here. So we're going to now go through a couple of steps to turn those features into one logical Dask array. We're going to convert each feature into one Dask array with a single chunk. So usually a Dask array is composed of many different NumPy chunks. Each of these Dask arrays has just one NumPy chunk, the one for that particular day. So you can see here its shape is the same shape that we saw before. And now that we have many Dask arrays, we can use the standard Dask array library to concatenate all of these smaller Dask arrays along this first axis, along the time axis. So we see here that the shape is increased along the time axis. And so this is one, so X here is a Dask array object, and it is one logical array that is comprised of several NumPy arrays that are scattered in various parts of our network. But it still looks a whole lot like a NumPy array, so we can ask for how many bytes it is. It's about 4 gigabytes. So we could conceivably do this all in RAM on a single machine, but we're choosing to do it on a distributed machine just to show off some timings. And we can do the sort of standard things you normally do with NumPy arrays, as long as you add this compute method at the end. And when you call this, it's actually going to reach out to the cluster, coordinate all of those NumPy arrays to do all of that work, and come back at you with the answer you expected. So start looking at timings. So we're going to look at a few different cases that have varying complexity, and we'll see how fast they are and how that influences performance. So here we're getting out just one element of one slice of our array, and we get back that answer in around 10 milliseconds. So this is probably bound by the network round trip, going from the client to the scheduler to the worker and back. If we look at getting out one time slice, this is about 100 milliseconds. It can go up to about 200, 300 milliseconds sometimes as well. And this is bound probably by bandwidth. So one of these slices is roughly around 8 megabytes. This is probably those 8 megabytes coming through the network. If we compute the mean, there's very little bandwidth here, but it still takes some time. And this is probably because of scheduler overhead. So computing the mean of a single NumPy array is quite fast, but we're probably bound here by the scheduler doing all of the coordination among all the many NumPy arrays, because this requires us to touch all of our data. Computing this number requires us to touch every single number that we've loaded into distributed RAM. Okay, so now that we have our data set in RAM, it's quite nice to play with it and interact with it. Let's increase that size a little bit. And so what this IPython interact widget does for us is allows us to play with this slider, and as we move this slider, we will select a different time slice of our data. That time slice will come in, and we'll get to see it locally. So now we're combining an interactive human element, this widget, with distributed computing, with reaching out to our cluster and pulling in the right data set. So you see here on this particular day, it looks like Northern Africa was fairly hot, hotter than the rest of the world. No large surprise there. This seems to take around a couple of seconds for every refresh, which is surprising given that we saw that bringing in one time slice only took about 100 milliseconds. It turns out that we're bound here not by cluster computation or bandwidth. We're actually bound here just by rendering this image, it seems. So if we reduce the size of the image, we actually are quite a bit snappier. Just to show off that performance difference, just to sort of properly show how fast the distributed system is being, let's look at and verify again that we can bring in one of these time slices in around 100, maybe 200 milliseconds. And as long as we're not rendering things are actually quite fast. So as a counterexample, let's go ahead and take that same time slice, but rather than render it to the screen, let's compute the mean and render that to the screen. So it's much easier to both move the intermediate result to local machine and to print this number. And what we're going to see is that this is quite fast. So the delay between me selecting a different point on this slider and this number changing is quite fast. It's roughly invisible to the human eye. In fact, we can take this slider and move it fluidly, and these numbers will change fluidly. And at every change in the number, every movement of the slider, we're actually interacting with the distributed cluster. So it's a very interesting case of a human interacting with a human element, this slider, triggering many hundreds of computations on the cluster and getting responses back in, again, sort of the 10 to 100 millisecond scale that looks invisible to the human eye. Okay, so this example was actually a little bit easy because we were slicing along this first axis, this time axis, which happens to be how our data was laid out. So we only have to touch one partition in order to get this data set back. If we want to make things a bit harder on ourselves, we might slice and set across latitude, so that every selection of latitude still requires us to touch every piece of our data. So this is a bit harder on us. We're trying to do the hard case. But even in that case, we're still decently snappy. This is happening in the couple hundred millisecond latency. So it's not quite fast enough to get a totally fluid experience as we scroll by, but it's still pleasant for interactive use. Okay, so to have some fun, let's normalize our data set. So a lot of what we were seeing before in the previous images were things we recognize, things like the continents and things like the fact that the equator was hotter than the poles, right? It's sort of warmer in here than it is at the top and the bottom. But we can get a lot more information out if we normalize that data out. So if we subtract off the mean over time here, so if we subtract off the mean over time and then divide by the standard deviation, we can get something like a z-score. This will give us not the temperature at a given point, but how unexpectedly hot or unexpectedly cold that temperature is for that particular time of day, that particular time. So great, we've done that computation. And now we can look at our data set. And we see now that the steady state has been subtracted off, and we only have the sort of interesting interactions that are happening inside the climate. And so again, we can sort of interact and explore this data set. We can see interesting features happening along the equator, these sort of ripples that are happening. We find regions of high contrast. We have very, very cold regions next to fairly hot regions. So there's lots of interesting meteorological weather phenomena happening here. And again, this is really interesting because we were able to interact with this data set in a really human timescale way that makes it more visceral to us. And we can really start to drill down into what this data set looks like at a broad scale. So again, sort of one of the first times in which we've been able to couple n-dimensional array data, which is sort of complex to deal with, and efficient distributed computing so that we can align human interactivity, distributed computing, and science all together and sort of gain some insight quickly. Okay. But again, in this computation up here, we're bound not by pulling data down, we're actually bound by rendering this image. So we should be working more on image rendering inside the browser. Maybe the browser isn't the right place to do this. Maybe we need a rich client. But to sort of show off, again, that we can do this faster, let's render not an image, but just this plot, where now we've averaged out over longitude, and we're just showing the temperature by degree latitude. So here we see the southern climates, and here we see the northern climates for any particular time slice. And we can sort of scroll this around, and we can see how the temperature changes in the beginning of the year. It seems like the southern climes are warmer than you'd expect. This is northern winter, southern summer, so this makes sense. As we move towards the end of the year, we see that trend start to reverse. So that all makes sense. And again, we're sort of interacting with this at human timescales. Great. So again, what we've seen, we've used SunGridEngine, network file systems, and NetCDF together with distributed Dask arrays to interact with weather data in a way that could scale out to much larger data sets, and in a way that was comfortable for a programmer who was used to NumPy, and in a way that was fast for a human scientist. We experimented a little bit with timings and showed off what was good, what was bad, what was slow and fast. Just to be honest and show some things that didn't work. So there was no single high-level read HDF5 function. We had to go through a little bit of work with futures and this executor map function, which seemed a little bit low level. It'd be nice to expand that and really improve some of the user interface for more novice users. We really need a larger problem. So this data set you could conceivably do on a MacBook Pro in RAM without a distributed cluster at all. But there are many problems that are at sort of the terabyte scale for which interactive computing would be very powerful and yield novel science. It would be nice to automate the deployment of these sort of workers and schedulers. In particular, if we look over here what we did with SunGridEngine, this all seemed fairly straightforward, but I had to do a little bit of hunting around to find the right keyword arguments and how to just send off a worker without any sort of time thing. And while SunGridEngine is fairly widely deployed, there are many other systems like Slurm or Torque or the use of PBS scripts that are as widely deployed. And it'd be nice to find some way to, again, automate this and make this easier for novice users. Finally, most Dask array use today is on single machines on out-of-core data, and most of it happens through the X-array project, which provides excellent n-dimensional labeled arrays, particularly common in climate science. And it'd be nice to integrate the same distributed work into the X-array project. Okay, great, that's it. Some final links. If you're interested in Dask, you can go to dask.pydata.org. Dask is the parent project. Particularly includes documentation on Dask array and sort of the whole project as a whole. You can also go to distributed.readthedocs.org. This holds information on the distributed memory scheduler, which is allowing us to use a cluster. Finally, I'm blogging about this on my blog at matthewrocklin.com/blog. I also recommend going to two pages. This is the page for a star cluster at star.mit.edu/cluster. This is what I used to start up my cluster as I was playing with this. They have a very nice screencast here. It's 8 minutes long, and it totally sets you up with running a cluster on EC2. Finally, I'd also like to give a shout out to the X-array project at xarray.pydata.org, which is a great way to interact with climate data, and it uses Dask array under the hood, and it's a fantastic way to interact with these data sets. So that's it. Thank you for your time.